appreciate you coming to Argen's one of our lectures today. Hope you've had a chance to see outside. We have a whole list of lectures. We have a lot of great topics for everybody. I just want to introduce Paul Cascone, and then I'm going to sit back in the corner and let Paul take over. So, Paul Cascone, some of you may or may not be well aware of this, but Paul Cascone has really been kind of the, I would say, the inventor or father of alloys. And so he set up many, many years ago probably more patents for alloys than anybody. And then Paul likes to say he's outlived a lot of his patents. But that's where Paul really kind of became part of our team at Argen, and he is head of R&D at Argen. But what a lot of people don't know is Paul, not only is he a metallurgist, but he also is a ceramic engineer and has PhDs, advanced degrees in the subject matter. So Paul, over time, as the industry evolved and as our company evolved and we moved away from alloys because the market changed, Paul's skills and backgrounds were very transferable into Zirconia. And so Paul has really become, if you will, the designer, the founder, the maker of the special sauce of our entire Zirconia portfolio. And we found a need in the marketplace a couple of years ago to educate people on how to handle Zirconia. We found that a lot of people didn't really understand some of the nuances, and there's still a thirst of knowledge that people want to get. And so Paul has had a great series of lectures to do that, and we're very excited to have him here today do it in person. And so when Paul's done, on our website at argen.com, under Argen University, we have a whole series of other of his presentations that talks about this subject matter in different forms. So I know you're going to love what he's going to talk about, and if you want to get more of it, I would encourage you to go to our website and go to Argen University. Paul, did I leave anything out?
No, thank you. Thank you
so without further ado, we have to refer to him as the Don, Paul Cascone. So thank you very much, everybody.
Good morning. Good morning. Thank you, Michael. Thank you for that introduction. Very nice. So today we're going to talk about zirconia science, and I give a byline, what you should know in 2019, because this is an updated version of some of the other ones you may see on the website. I've added a lot more information with regard to processing, and that's because those are the kind of questions that we're getting. So we want to be able to provide you with exactly what you're asking for with regard to understanding the material zirconia. So we're going to touch on where zirconia comes from, the nature of zirconia, something called the Y classification of zirconia. A number of months ago, maybe one of your clients asked you about this, and we'll talk about what it is and where the terminology came from. I'm going to talk about the newer dental grades of zirconia. Not every zirconia is the same. And we're going to talk about why and what's in the marketplace now, and maybe what's coming up soon. Coloring zirconia, the different options you have, whether you want to do a dip zirconia, whether you want to do appreciated zirconia or multi-layer. We're going to discuss how those are developed and how those can be used to their best indication. And we're going to talk about how zirconia processes this. We thought you might enjoy seeing how we do it in our factory in San Diego. And learn why zirconia fractures, minimizing laboratory failures in both the laboratory and the operatory, what you can do to do that. And then finally, this is very new, the CRA report in October of 2018 discussed the 5 common mistakes for dentists to avoid in zirconia. And I'm sure you're going to find something in there that you could use the next time you speak to one of your clients. Okay, so the nature of zirconia. What is this material? Zirconia comes from the mineral zircon. And zircon was one of the first minerals to form in the Earth's mantle 3.5 to 4 billion years ago. And it's found on every continent. And in some cases, it's found very close to the surface. Now, what's unusual about that is that zirconia contains radioactive elements. Now, radioactive elements generally are only found in materials that are very deep in the Earth. So what you're seeing here is a computer simulation of what was going on the Earth 3.5 to 4 billion years ago. And what was happening was that asteroids, and many of them, were impacting the Earth. And these asteroids were very large. Some of them, state of Texas, size of the state of Texas, hit the Earth. And when something that big hits the Earth's mantle actually melts. So anything that's underneath gets pushed to the top. And that's how zircon got to the surface. One interesting point, recently NASA discovered a piece of the Earth on the moon, a moon rock that was brought back from one of the Apollo missions. They classified it that way because they found zircon crystals in there. The chemistry of the moon doesn't allow for the formation of zircon, but the chemistry of the Earth does. So that's an interesting, I thought it was an interesting one. Now, zircon is nothing more than zirconium silicate, and it has a significant amount of zircon, and then this other little element here, we'll talk about that in a minute, and silica. And those are the major parts of the sand. And here's the sand. This is what it looks like. This is the major mine in the western part of Australia. This is Jack Hill's part of Australia. And this is the most economical mine in the world. The second most economical one is in Brazil. And there are a couple scattered across every continent. But for the development of a usable material, this mine is the best one. And you can see it's very close to the surface. It's an open pit mine, so it's a very easy access. And you can also tell there's nothing else there. And there isn't anything else there. This is the oldest part of the Earth, and it's a very inhospitable climate to anything growing. This part of the Earth was the least impacted by any type of erosion, whether it be wind or rain. So they find zircon crystals here as old as 3.5 to 4 billion years ago, and it's very, very interesting. So in order to get rid of this stuff, here you have a radioactive material called thorium, and here you have the radioactive material uranium. Now we're familiar with uranium being radioactive, but not necessarily thorium. So how do you get this stuff out of here? You just dissolve it in acid, which is an aggressive process. Dissolve the entire thing in hydrochloric acid, and you make something called zirconia hydrochloride, oxychloride, I'm sorry. And that's what this is here. And it's just a big slurry, just a big solution. In the formation of when the material gets dissolved in the acid, all of the elements, the trace elements, the thorium and uranium drop out. So you could get very pure zirconia using this process. But you can see there's a significant amount of water in here too. Okay? Now, zirconia is a very unique material in a variety of different ways. And as a dental material for prosthetics, it's very unique in that the processing of the material determines the properties of the material. And you'll see in a minute, other materials that we're used to, that's not the case. So here we can have large crystals, and we could take that liquid and mill it and make the crystal smaller. And if we do that, we're actually going to impact the optical properties of the material. The finer crystal materials will actually develop a more opacious material than the larger crystal materials. So we have to control that crystal size. That's number one. Number two, how do we add the yttria? Yttria is added in order to stabilize the material and give it some translucency and some strength. By itself, zirconia is extremely weak. So in order to do that, you could do it in a number of different ways. And I'm showing the way we do it. We add it as a chloride to the original mix. Now you don't have to do it this way. You could add it later on as an oxide and just do a mechanical blend. But adding it in this stage gives it the ability of having a more intimate relationship with the zirconia. And that, we find, improves the translucency and it impacts the strength. And we'll show you that with our HT Plus material. Now, you're starting up with this slurry, and there's a variety of things you could do to it. You could take that slurry just as it is, and you could slip cast it and make the disc. And that's called gel casting. And we're going to talk a little more about that. Or you could take it and add a binder to it. Now, the binder is nothing more than a plastic. It's an acrylic type material. And the reason why you want to add the binder is so that you can press it into shapes. And that's what this looks like. When they take the binder out and they get the water, I'm sorry, when you add the binder and take the water out, you wind up with these nice, beautiful spherical particles. They're very uniform in size, so they're very easy to press and they flow very well. And that's important for when you fill the press. So you have three basic processes for processing zirconia from that slurry. One is just take the slurry and allow it to sit in a mold and just cast it as is. That's called sedimentation. So that just sits there. Now that is very good if you're using a white product that you do not intend to color. And that's what we had. That's what we started with. That was like the zircon material. That was like the original lava material, or the original Bruxer material. The original Bruxer material was made using this process. The problem with this process is that you can't color the material very easily. It's almost impossible to penetrate the resultant gel casting with a coloring liquid. And also, it's very difficult to get a shade that's going to be consistent if you start using the coloring oxides. So the next thing is to use water and electricity. And that'll also produce a dry powder, which you could then press, or water and temperature. This is the process that we happen to use. And this also produces a dry powder, and it produces those particles that I just showed you before. Very nice, uniform particles that are easy to press. Now, when we look at the other materials that we've been using in prosthetic dentistry, we find alloys and porcelain. Those are the basics from the mid-50s up to the early 2000s. And how do you modify an alloy? Well, you change the composition. You want it white, you add a little platinum or palladium. You want it yellow, a regular casting gold, you could add copper to it. You want to make it a porcelain alloy, you take out the copper, take out some of the silver, and add some other elements in order to make porcelain bonding. But no matter which way you look at it, you're modifying the composition. The processing is very difficult to modify. The only thing you can really do is grain refine it. So with an alloy, we modify the composition in order to make it better or make it fit what we wanted to use. You remember back a number of years ago, you had different porcelains with different thermal expansion coefficients, and you had to make sure that the alloy you used matched that porcelain. So you had to make the alloy in order to fit that particular category. And you did that by changing the composition. Likewise, for the dental porcelain, we had a number of elements, and these 6 elements were all you really needed to make a wide range of porcelains, from the luminous porcelain that was able to be made in a single unit, to very fine-grained porcelains with beautiful aesthetics. You modified the composition by just modifying just a couple of elements. However, they have very significant impact. And you couldn't do much on the processing side, except if you slow cooled it, well, then the porcelain thermal expansion raised. And that's why, like Vita porcelain, took advantage of that. They made the porcelain to be a low thermal expansion porcelain, and then said, okay, if you're using an alloy with a high thermal expansion, you can slow cool it, and the compatibility would be assured. So they took advantage of that, but that's about the only thing you could do with porcelain. You had to change the composition in order to make any significant changes to the material. For zirconia, however, we have a very limited item we could add or subtract out of the material, and that's yttria. That's the only thing that we could really modify the composition and get a significant amount of difference in properties, whether they be mechanical properties or translucency properties. What matters is the processing. So we have the quantity of yttria change, how you add it, whether it's added as a chemical addition or an oxide addition, the type of mechanical milling you use, if you use any type of mechanical milling, the mixing method of the yttria in there. There's a variety of different ways of mixing it. If you use a big ball mill, or you could do a blend that I'm going to show you in a minute. And then finally, how the discs are fabricated. The drying method is also important. As I said, there was electricity or temperature, and then how the discs are fabricated. So we're going to talk about how Argen processes the disc as well. Now, zirconia is unique in that it looks like porcelain, it's whitish, but it doesn't have that internal structure of porcelain. It is not a glass. It is a crystalline ceramic. Just like alloys, it has these grains, and you have grain boundaries. And that causes a lot of the problems that we see with zirconia, and it causes us some difficulties in processing it. We can't be as cavalier with zirconia as we were with dental porcelain. With dental porcelain, we had 3-unit bridge. You could build it up in a big lump, fire it, and then grind in the anatomy. You can't do that with zirconia. Zirconia does not allow that to happen. Also, the zirconia is very sensitive to thermal shock, and again, due to the fact that it has this crystalline structure. And we're going to talk more about that. So the properties of the zirconia material is determined by how much yttria is added, how and when the yttria is added, the particle size of the zirconia itself, the process used to make the powder, and how the discs are fabricated. So you could say, okay, I got a high translucent porcelain from this company and a high translucent porcelain from this company. Why don't they behave the same? Why don't they look the same? Well, now you know why, because they were processed differently. Now, one of the beautiful things about zirconia, and it's very, very unique, and we take advantage of this property, is that it shrinks isotropically. That means it shrinks in all 3 dimensions uniformly, independent of its mass. So what I mean by that is you can have a 3-unit bridge with a very heavy pontic, and all 3 sides will shrink uniformly at the same rate. If you did that with an alloy, tried to sinter that alloy, you wind up with a horseshoe, because the sintering in the pontic would be greater than the sintering on the abutments. So they'll just pull the abutments up. Okay? We don't have that with zirconia because of this one property. And this one property was used early on in the 80s for developing these things that are called ferrules. And it's nothing more than a tube of zirconia. And you see, it's a relatively small tube. And what they were used for was joining fiber optic cables. You may remember in the 80s, a lot of communications companies were laying this fiber optic cable. The next generation of communication was going to come over fiber optic cables. Well, fiber optic cables are nothing more than a glass strand. And when you're going to come to an end of a glass strand eventually, and you have to join them together. But when you join them together, they have to be joined exactly. The surfaces have to be parallel and flat, and they have to be joined exactly together. And zirconia was chosen for this because it shrinks isotropically. If you made this little ferrule out of alumina, which they tried originally because it was less expensive, this side may actually be a different diameter than this side. When you do it in zirconia, it's perfect. It's perfect. So a lot of companies got into the business of making these little ferrules, and this is all it looks like is a fiber optic cable this way, fiber optic cable this way, and the little tube in the middle, and that's where they join together. It's a very simple application, but it's extremely difficult to make these things. One of the biggest problems is making sure that this inside surface is polished. So you had to use diamonds, because diamond is the only thing that injures, so to speak, or damages zirconia. There's no other substance that does it. Zirconia is second in hardness only to diamond. Now, the next application were hip implants. And these little ceramic balls were made out of zirconia, very similar to the type of zirconia that we use in dentistry. And it was a very good success for about 15 years. And then they started having breakage. And the breakage was identified from one company, one lot. And that particular lot was the first lot that came out of a special type of oven that they were using for sintering the zirconia. They wanted to try and sinter it faster. Can you believe that? We wouldn't do that, right? We would never want to try and sinter zirconia faster, right? Yes, that's a joke. But by trying to improve the sintering speed, even though the material passed the quality control test, there was a structural imperfection in the interior of the material that caused the fracture. So that killed that industry. The dental compositions for zirconia are very, very simple. They have yttria additions between 5 and 10 weight percent, and the yttria determines most of the properties, as I said before. Then you have this little element here, this little oxide here called hafnia. Nature does not allow some products to be 100% pure. You're always going to find a little bit of nickel and cobalt, and you're always going to find a little bit of iodide in salt, and you're always going to find hafnia in zirconia. It's just the way it is. But it's benign. It doesn't have any impact on the properties of the zirconia, as long as the hafnia content is brought down below 5 weight percent. And everybody has that. That gets done very early in the process. Then there's this other element, alumina. One of the reasons why the original zircon or lava materials were so chalky white was because they needed that they added 0.25% alumina into the composition. That 0.25% alumina was the result of the testing that they did to determine why those hip joints failed. What they found with the hip joints was that the body fluids, water, was getting pushed into the grain boundaries of the zirconia. Remember, I said zirconia is a crystalline ceramic. It has crystals, it has grain boundaries. You saw it on the picture. So water was getting forced into the grain boundaries and actually destroying the strength of the zirconia. By adding a little bit of alumina, and the first addition that they tried was actually 0.25%, they found they could eliminate that problem. So they left it at 0.25%. And that's what we started working with. We started working with these materials that were a substitute for the metal coping, a metal framework, just a zirconia coping, a zirconia framework, and you bake porcelain or press porcelain on top of it. That's why that material was so white, because of the aluminum. Now, in order to make zirconia into a monolithic material, where the entire crown is going to be made out of the material, you have to make the material more translucent. So that means you had to reduce the alumina content. Some of the early materials that were put out in the industry actually had no alumina at all. And there was some concern that the failures that were present in the hip joint may actually occur in the dental restorations, but that didn't occur. But we still were concerned about the aging over some time, because let's face it, it's only been since 2004 that we've been using zirconia. It's a very short period of time. We've been using alloys for over 100 years. So our concern is genuine, and what we found was a way of getting the alumina in the grain boundaries, but reducing the content generally down below 0.1%. And at that point, the material becomes translucent, and at that point, that was our starting material. And some of the newer materials, we actually have the alumina down to 0.05%. Very, very small. It's there as an insurance policy to make sure that the aging doesn't happen, but it's there. Now, there is a standard for zirconia, and this standard is used by the FDA and used by ISO for CE mark. And this standard is called 6872. It was last updated in 2015. But this was a standard that was developed for dental porcelain, not zirconia. There hasn't been a standard that's been developed specifically for zirconia. And there are implications of that. So what happens is this standard has no compositional requirements. The manufacturer is under no obligation to tell you what's in that zirconia. It has a limited mechanical property requirements, because the mechanical property requirements were developed for the aluminous porcelain back in the 1960s. And that were, number one, for a 3-unit prosthesis involving a molar, that the flexural strength has to be at least 500 megapascals. Or for 4 or more units, 800 megapascals. Well, you may have experienced that that doesn't work for zirconia. The material has to be a lot stronger than 800 megapascals in order to make more than 4 units, especially when you have 2 pontics next to each other. It has to be at least 1100 megapascals. The other thing, and this really bothers me, is that the radioactivity test is for uranium, but not for thorium. So we know that there's a radioactive thorium in the material, but yet the standard doesn't address that. So what does this mean? Well, what it means is that zirconia products can obtain FDA or ISO CE certification, meet the standard, and still have some radioactivity in it, and still have poor mechanical properties that are made for that indication. And we see some of that material in the marketplace. So just because the product is 510K approved or cleared, that does not mean that it's the best you should use. Now, this Y classification of zirconia came about from some lectures that were being given by Rella and Gordon Christensen. And they talked about this in their lectures, and they said specifically that there was a 3Y zirconia and a 5Y zirconia, and the 5Y zirconia, in their testing, they found had some fractures, where the 3Y did not. The fractures they were referring to were not fractures in the mouth, but were actually fractures at the dental operatory when the dentist was contouring or adjusting a contact on the zirconia, and we're going to see some of those. But what this 3Y, 4Y, 5Y means, this is just a chemical shortcut that's used by the ceramic industry to indicate how much of that yttria is in there. So 3Y means there's 3 mole percent yttria. Generally, that means it's about 5.5 weight percent yttria. 5Y means it's 9.2% yttria. And then 4Y, right now we're the only ones that have this 4Y out there, and that's about 6.9% yttria. So don't get confused over that. If your client asks you how much yttria is in your material, just if you don't know, I'm happy to provide you with an answer. You can just email me and you'll get an answer regardless of what product you're using. Remember I said in the standard, the companies do not need to provide the compositional information. So when this topic first came up, some people never got an answer on how much the yttria was in their zirconia because they couldn't find it in the literature, and there wasn't any. So the different companies have addressed this in different ways, and we provide you with all of that information, and most of the other companies like Dentsply and Ivoclar do too. Now, we have different types of zirconia. We have the original, our brand is called Ultra, and that is the original type of zirconia that was introduced. That's the opacious material that's used for copings and frameworks, and porcelain is baked or pressed on that. And that strength is very, very high, 1,400 megapascals. Maybe it's even a little more. And remember that, because we're gonna come back to that later. And then there's a high translucent zirconia, and we call ours aesthetic, and that has a strength of about 1,100 megapascals, and that has a translucency of about 40%. And then let's jump down here to the interior. Then the next type of zirconia that was introduced were the interior types. You saw Argen interior, so Bruxer interior, and these were the higher yttria content. Those were called super translucent, and the strength dropped, but the translucency went up. So a lot of people thought, well, okay, in order to get the translucency, I have to sacrifice the strength, and we didn't accept that. We wanted to develop the next generation of zirconia, and we wanted to improve the translucency, maybe not as much as the 5Y or the interior, but better than the high translucent material. And we wanted to keep the strength the same. We didn't want to lose that 1,100 megapascals. Well, through our processing, we actually found a way of increasing the strength a little bit and may increase the translucency as well. And that's called our HT plus material. And this is somewhat unique, and it also is very popular. So we're going to see more types of zirconia introduced in the marketplace in the coming years, and we have to learn how to handle it. Most importantly, we have to learn how to communicate it to our clients. because there's a thought out there that wall zirconia is the same, and there's also a thought that wall zirconia is indestructible, and that's not true. Shade into zirconia, the first way is dipping it, and the way this works, you take the zirconia, the pre-sintered zirconia after it's milled, and you put it in a coloring liquid, and this gives you the most control to produce a transitional effect and whatever effect you want on that case. The aim is to best individualize the case. How it works, the liquid that you dip it in contains metal ions that combine with the zirconia at a high temperature to produce a color. And like iron, for example, will produce a color from yellow to brown, depending on the concentration. Chromium can produce a color from green to red, depending upon how we make the solution. And erbium produces a nice pink. So you could blend those materials in and see and develop the 16 or 19 different shades that we have in the Vita shade color. The negatives about this is very dependent upon the practitioner, whoever is doing the dipping. You could get two restorations that are identical, and you do it at two different times, and the shade may not match. In order to address that, we have, in our digital center, we use these little jewelry cleaners, and we dip the units in at the same time and take them out at the same time, so that the shading is going to be identical amongst those units. The result on this, the results may be inconsistent. You may see some inconsistency from time to time on the shade. You have to make sure you keep the lid on the liquids closed so that the water doesn't evaporate. If you allow the water to evaporate, your colors are going to get more intense. Then there are pre-shaded or shaded materials. Here, the benefit is consistent shade. It's most consistent for bridge work. The coloring metals are added as oxides with the zirconia powder and blended together. So they're available at high temperatures and produce the shade. And there's not too much negatives about this, but it may need some staining. And you could use the incisal enhancer and get that transitional effect as well. The only negative that you could think of is that, well, your inventory costs are higher because now you have to stock all different shades. Then the next thing is multi-layer, and these have the automatic transitional effect because the composition of the materials actually vary from layer to layer. So you just have to be careful how you mill it, there's an incisal up, and how you nest it. And there's the nesting is critical, and this also has the highest inventory cost because now you have different thicknesses depending upon the size of the restoration you're making. So for dipping, you have a difficult case like this. It's best done by dipping and then doing your characterization. Here you have a case where the pre-shaded zirconia is best because you have a bridge and you're able to maintain the same chroma level across independent of the thickness. So you're going from a thin abutment to a heavy pontic back to a thicker abutment, and the salt same shade. Now, also when you're judging the zirconia, make sure you put it on the die, or else you're going to see a shade much lighter than it's supposed to be. Okay? And this is an example of that. So now we're going to talk about how Argen processes this, and we start with blending. As I said before, there's different ways of doing the blending, and this way is the simplest way to avoid any type of problems. Typically in blending ceramics, you put it in what's called a ball mill and you just spin it. But zirconia is like a martini. If you spin it too hard, you're going to bruise it. And zirconia gets bruised, the particles impact each other, they form a hard particle that does not color, or it may not sinter properly, or it may not mill properly when the mill hits that hard spot. So we use this type of a blender. It emulates a hand blending operation. It's slow, but it's thorough. And it gives us a very good blend in a very, a little longer period of time, but it avoids any type of bruising of the zirconia itself. Then we take that material and we put it in a hydraulic press, And this happens to be a digitally controlled hydraulic press. And the reason why we want it digitally controlled is because we want to control the rate at which the die, which is here, comes down into the upper die comes down into the void and presses the powder. We don't want to bang the powder hard. We want to do it gently. And we make a disc. And as I said, we can make the disc because of that binder in there, that acrylic holds those particles together. So now we've made the form. The next step is to put it in an isostatic press. We literally just stack them all up. You put them in vacuum baggies and stack them all up. And what happens in the isostatic press, this is an oil-water mixture, and this is you can see just the edge of the cylinder itself. It's a cylinder that's about that thick around because we put it under very high pressure. And as you're aware, liquids are incompressible. So that pressure goes on all three sides of the zirconia disc and makes the disc uniform in density. And that's important because when you're milling a bridge, you don't want one side to be a little looser than the other. You want it very uniform. You want that milling to be consistent. And then they go into a kiln. And in the kiln, we do two things. Number one, we remove the acrylic and we bring it up to a higher temperature so that the particles can stay together. That's called a pre-sintered state. So stay together just enough so that you can mill it. This is a 70-hour process. When it goes in the furnace, it stays in the furnace for 70 hours. The heating rate is extremely slow, less than 15 degrees an hour. And the cooling rate is even slower. Zirconia is very sensitive to thermal shock, especially in this condition, in the pre-sinter state. It's very frail. So when it comes out of the kiln, it's stronger. You can handle it. We turn. We're gonna see. We turn the step in, and then you can mill it. Here's where we're turning the step in a lathe. That's Robbie over there, our little robot. Robbie is a very lazy robot. And then when it comes out of there, you see the step has been ground in. That's a support for your mill. And these are little lasers that measure it. So we weigh it. There's a station to the left over here. There's a station to the left where there's a weighing station. It goes right into the computer. The measurements are taken in like less than 2 seconds. And we measure the height, the width, the diameter of the top, diameter of the middle, and the diameter of the bottom. And that calculates the volume. From there, we combine that with the weight, we calculate the density. So this is the density of this piece. We know what the final density is going to be, so we can calculate the shrinkage rate. And on each of our discs, you're going to find the material type and size, 9812. You're going to find the lot number, and then there's a dash and a number after the lot number. And that dash and the number after it is the number of discs in that work order. So this is the 90th disc in that work order. This is the 89th disc. This is the 88th disc. This is the 87, 86, and so on. So we keep track of each disc. Most other companies just keep track of it by lot. And we calculate the shrinkage rate for each disc as well. And as you can see, the shrinkage rate only changes in the 4th decimal place. Very consistent. We also put on a 2D barcode, which has all of this information plus more for traceability, and then finally the material indicator in big type. Okay, now we're going to talk about processing zirconia, both the milling, the sintering, and contouring. So when we mill zirconia, sometimes We mill too fast. Now, how do you know you're milling too fast? You're getting chips. Getting chips at the margin, getting chips. Sometimes I'll show you one where you're getting chips actually on the outside. And all that means is that, no animals were hurt filming this one. He does that all the time. So for your mill, number one, we suggest you calibrate the mill frequently. There's nothing wrong with calibrating it every day. It's a very quick process, and it'll save you a lot of time, especially on bridge work. Because if your mill is out of calibration, that's when you're going to see it. The bridges are not going to fit properly, and it's because the machine is assuming when it flips it over, it's going to be coincident with the original side that you had. And unless it's calibrated, it's not going to be coincident. So it's not going to be milling in a straight line. Check the milling strategy you're using. The original, depending on how old your mill is, you may have a milling strategy that was designed for the higher strength material at 1400 megapascals. And that material, you could mill really fast. But when you come to the monolithic, you want to slow that down. Now, you're not going to see any significant difference in the time it takes for you to do the milling. It's a very small increase in time, but it's a big difference to the zirconia on the feed rate. How not the speed of the mill, how fast that end mill is being pushed through the material, the feed rate. That's what you have to pay attention to. Okay? If you're getting any chipping, then slow the feed rate down. Learn how to use your CAM program. Every CAM program now gives you the ability of changing it, because most of them are now open source. Or you can go back to the manufacturer and ask them to provide you with a slower feed rate. Okay? If large bridges are not fitting, as I said, one reason is that the calibration is off. The other reason is that your tools are dull. Zirconia, I said from the beginning, zirconia can only be damaged by diamond, which means zirconia is damaging everything else. Zirconia is much harder than the end mill you're using, even if you use a diamond-coated end mill. So it's going to wear that end mill down. And when it wears it down too much on a bridge work where you get a significant amount of span, you're actually going to be off the size. So it's not going to fit properly. Check the tools for wear and replace it when your software recommends a change. Most of the CAM programs will actually pop up and say, okay, we've had this amount of hours on this mill, change it out. Do it then. Don't wait. Don't try and get another disc out of that end mill. It's not worth it. You're going to be wasting more time and more money on the disc trying to get it to work than on the end mill, than replacing the end mill. And also keep the disc support, the area where the disc goes in, keep that free of zirconia dust. That's the biggest reason for fractures, and we're going to see some of that of the disc itself during the milling operation. Okay. Now the milling parameters, we have a material block, and we have a tool that's going into it. The factors are the spindle speed. The radial depth of the cut is depending on the tool diameter. So you're doing roughing at 2 millimeters and you're doing the final one at, let's say, 0.6 of a millimeter, and you have a 1 millimeter in there. That's the reason why you want to take off smaller and smaller materials, because you want that surface to be finer and finer. Okay? The axial depth of the cut is how much it actually is digging into the zirconia, and then the feed speed, how fast is that being pulled in, being pulled across. The XY direction, that is where you're going to get chipping. And that is where you just need to go into the CAM program and just lower the feed rate if you see chipping. The other thing I wanted to talk to you about is end mills. End mills are very sophisticated devices. They have things called flutes, and that's the cutter. How many flutes are on an end mill matters. You shouldn't use the same end mill for zirconia as you're doing PMMA, because for PMMA you need a single flute device. because you don't want to cut that much material. The zirconia, you could go a little faster and it'll cut it a little deeper. My point is that there are a variety of different parameters that go into an end mill. And there are things that you can do to reduce the cost of processing the end mill that impact these parameters. Sometimes you can get what seems to be a good deal on an end mill, and you try it and it works okay first few times. But then you notice that it stops working very well. It starts dragging and you start getting some chipping. That's because the design of the end mill is not allowing the zirconia particles to get pushed away. That's what this is for. That's what that length of cut is. The zirconia particle gets cut at this edge, and you see this edge has a variety of different angles and cutting edges to it, and then the zirconia powder gets pushed away as the flute goes across. So the cheaper end mills, it's not just a matter of how many people handle that sale. It actually could be due to the design. So sometimes buying a cheaper end mill may not be in your best interest. Now we see this a lot. With a ring or without a ring, you can get chipping due to excessive clamping forces. Now this clamping force is due to a variety of things, depending on the type of mill you have. On the Roland D50, the manufacturers were very smart to include this gasket. As long as this area was kept clean, the disc is going to sit flat in the support, and that's good. If you allow the dust to accumulate in there and don't clean it out before you put the next disc in, then the zirconia itself is going to be at an angle, and some part of it is going to be under higher pressure than the other, and you may actually fracture the disc. But this gasket is very important. This gasket relieves a lot of stress, and if you have an older mill, sometimes these gaskets wear out. Replace the gasket. And if you don't want to do it through Roland, go down to your auto shop, buy a gasket material about a 1/16 of an inch thick, and cut it yourself. It doesn't make any difference what the material is, as long as it's a regular gasket type material. So it takes some pressure. And what it does is actually it's uniforming the pressure and making the pressure more uniform on the disc as you tighten it down. And you don't need to really squeeze it down very hard, just squeeze it enough to prevent the disc from moving around in the support. Now, if you have this type of a support, it's a little more difficult because this is metal on ceramic, and that's a little more aggressive. When you tighten this, do not go around. Do it as you would change a tire. You go across diagonally. And some of these machines now carry a torque wrench. Use the torque wrench. Pay very close attention to the torque wrench. And only on one click. Don't try and twist it again. It's not necessary to do anything more than to support the zirconia in the mill. You don't need to press on it like a superhero. Okay. Now this is the most aggressive type of clamping mechanism. Because it's all metal against the ceramic. And again, you can see a beautiful crack here. And that crack was because these two were tightened at a greater pressure than the other four. So this could happen, and it happens due to excessive clamping forces. Here you have a case I promised I was going to show you. Here you have chipping. This is the chipping during the roughing stage. The roughing, the milling strategy was set for the ultra material, the very high strength material, and this is a high translucent material, so it's not as strong. And what's happened is starts to chip where the roughing tool hits it first, and it chips all around. And the danger is when you have these implant parts, it'll chip right through it, and that'll render the part useless. So again, this is related to the feed rate, not the spindle speed. When you're removing the disc, but the units from the disc, most people use a high-speed handpiece, and that's fine. But just realize that a high-speed handpiece has a lot of vibration to it. So when you put that burr in there, number one, don't push hard on the burr. Let the burr feed through the zirconia, but don't go next to the unit itself. Go next to the disc. So you leave the two little nubs, your little nubs on there. See the end of the supports. Cut it this way because that will prevent the end mill from vibrating the zirconia disc and actually chipping it. And that chip you're not going to see until after it's sintered. Now, sintering zirconia, it's so slow. So slow. Hours. 7 hours for single units, 11 hours for bridges, maybe even 14 hours for bridges. Why is it so slow? Because zirconia does not conduct heat. Even dental porcelain conducts heat. Zirconia does not conduct heat. So it takes a long time to get up the temperature. And there are two critical temperatures. One on the way up at 1200 and one on the way down around 950. Cooling it through 900 to 800 is very critical. If you go too fast, you're going to crack it. And that's important when you're glazing. You have to make sure the glazes that you use are not 900 glazes. Use the 800 or 700 degree glazes. That'll eliminate a lot of problems. When you finish your unit, you glaze it, comes out of the glazing oven and it's cracked. It just cooled too fast, or your glaze temperature was too high. Yeah. On heating, we have to be very careful on heating because the furnace could be set for a heating rate faster than the furnace can really go. You could type in 90 degrees a minute, but it's not going to go up 90 degrees a minute. Why? Because it has to heat up that entire muffle and everything in it. And that takes time. That takes energy and time. That's what we're talking about, just energy and time. Also, the original zirconia, the ultra type zirconia, the high strength materials, it didn't matter very much where you sintered them. You could sinter them anywhere between 1450 and 1550, no problem. It still developed the strength, and it still, well, you weren't interested in translucency, everything was white. So that was good. Then when we went to the high translucent material, the 3Y material, the 5.5% yttrium material, a lot of people found that, okay, the sintering temperature was like 1550, but you know, if I went to 1570, it looked a little better. So people start creeping up the temperature a little bit. That's not true with the newer zirconiums. With the newer zirconias, whether they be the super translucent or the medium super translucent, the HT plus, you can't vary the sintering temperature too far away from our manufacturer's recommendations. If you do, the material will start to become opacious. So if you took a super translucent zirconia, whether it's anybody's, doesn't make any difference, whether it's Argen or Bruxer, doesn't make any difference, and take that and fire that at the same temperature you were firing your high translucent material, it would be opaque. It wouldn't have 50% translucency. It would be opaque. Because there's a transformation that happens to the cubic zirconia that's in the material, and that affects the translucency to the negative. So now you develop the translucency, then you lose the translucency as you go higher in temperature. So you have to be very careful when you sinter the zirconia. You have to do something very dramatic. You actually have to read the instructions. And just try and follow the instructions a little bit, okay? Let's reference it. Let's reference it.
The significance of the 950?
The 950 is the temperature at which the zirconia becomes very sensitive to thermal shock. Most of your programs are going to be slow at the 950 from the sintering temperature, let's say 1500 or 1550 down to 950. You're gonna naturally just put that down at 7 degrees a minute, 10 degrees a minute, something like that. But once people get below this temperature, they try and go a little faster. And 950 is very critical for the zirconia because it transforms at 950. And that transformation could cause a crack. And that gives you what we call a thermal crack. So that's why when you want to glaze it, you don't want to get close to 950. You want to stay below that temperature. Now, again, as I said, zirconia does not conduct heat. So what does that mean when you're processing it? When you're processing it, don't let the zirconia units to touch each other. I mean, I've gone into laboratories and I've seen these things, they just pile them up in there. It's not a good idea. Okay. And the other thing is, don't let it touch the side of the tray. Always keep a level of at least one layer of zirconia beads in there, but don't go too much. Don't go so that it just flops around in there. You want those beads in there. Remember I said it sinters isotropically, it sinters uniformly. That's why you want the beads in there. The beads allow it to just slide over. Now, one thing that happens to zirconia, especially if you're using a molybdenum disilicide heating element in your furnace, the beads will collect some garbage. And these heating elements actually produce a gas at 1500 degrees, and that gas will settle down on anything that's a little cooler. So that gives you two things to do. Number one, always use a lid. Most furnaces allow for the lid, use the lid. That'll save you a lot of time. You could wind up with actually one tray being totally useless if you don't use the lid. Use the lid, that'll solve that problem. The other thing is, if you're processing a lot of zirconia, that the pickup of this gaseous material will be very, very subtle on the zirconia beads. So have a little tray of zirconia beads next to your sintering furnace, and don't use them. Just keep them there for reference. So that's what white looks like. Because as these get used, they're going to go from white to a cream color. And you're not going to notice that. Your eyes are just not sensitive enough to notice when it goes from a dark cream to a light cream color to a dark cream color, or from white to cream. So keep the little tray of extra beads next to your sintering oven, so that when it come out of the sintering oven and it cools, you're able to see, okay, fine, now I need to change the beads. Again, it'll save you time. If you allow the units to touch each other or the beads get too dirty, you're going to start developing white spots on the zirconia. Yes?
Do you have any thoughts on beadless trays?
There are some beadless trays, and again, for short span bridges, they work fine. Now, as I said, zirconia is very sensitive to thermal shock. So what does that mean? That means that because it doesn't conduct heat, geometry is very important. So anytime you have a thick section next to a thin section, you have to go slower. And this is the main reason why the bridge cycles are so long, because you're obviously, you have a pontic next to an abutment. And here you have a thick section, very thick section compared to this thin section. But you also have a thick and thin situation when you try and use connectors that are just too thin. And here you have that situation here. There's a variety of different bridges, and they did the right thing by using these supports. However, the connectors that they used were too thin. And because they're too thin, they have a thin next to a thick and a crack. And some of the cracks extended into the restoration, unfortunately. So just be aware, thick to thin is difficult. Don't try and stuff 52 units in a disc. Use the larger diameter supports. That'll solve this problem. Now, rapid sintering of zirconia. Now, this is very appropriate for rapid sintering because you're taking something that's supposed to go slow and trying to make it go very, very fast. And I like Basset Hounds. Okay. So sintering, it requires energy and time. So we're taking something that says 60% dense, which means it has 40% air in it. And I couldn't get a good picture of something at that rate, so this is like half sintered. This is only like 10 to 15% of air. So air contains oxygen and nitrogen. And the oxygen molecule contains 2 oxygen atoms, and the nitrogen molecule contains 2 nitrogen atoms. Now we have to get that material out of this crystal. It's not like dental porcelain where it could evaporate. It has to go through the grain boundaries. That's the only way it's going to get out. So it has to travel through these grain boundaries. So what do? We have to have energy and time. Energy, because it has to have some excitation to move, and time, because you have to get it all out in order to get 100% dense. Now, as I said, the only way the gas is going to get out of there is through the grain values. If you try and sinter it too fast, you're going to leave some gas behind. And what happens, even if you're trying to do a really good job, you're going to leave some pores behind, and those are going to refract the light. So that means that your zirconia is not going to be as translucent as you expect it to be. Okay? If you go too fast, it's not going to be as translucent as you like. Now, there are circumstances where dentists don't care. So yeah, you could throw a couple of units in there really fast, and that dentist may not have any, may be colorblind for some reason. You don't know. They'll accept something other than what you would like to see, and that's fine for that application. We also have people that are using the higher translucent zirconia, rapid sintering it, and it looks like the low translucent zirconia. But as long as the shade is close, they're okay with that. And that's not a bad trick to do either, because you could actually get some strength out of there without sacrificing too much of the translucency. But generally, it's not a good idea. Okay? Anyway, but you can rapid sinter any zirconia. You just have to have the right furnace. And you have to have a number of things. And number one, for the furnace design, we would recommend you use a furnace that has silicon carbide heating elements if you want to do rapid sintering. And that's because the silicon carbide is immune to rapid heating and rapid cooling. Doesn't matter. The molybdenum disilicide, if you cool it too fast, it'll crack. So that defeats the whole purpose. Those heating elements, as you know, are very expensive, and you don't want to do that. Number two, you want a furnace with a small mass. Why? As I said before, you have to heat the whole furnace up, as well as whatever units you have in there. The other item is sometimes some furnaces have cooling assist. Like the Avoclar oven has a cooling assist, so you could actually, it actually bathes the furnace in cool air and air, so that it actually cools down a little faster. Because again, as fast as the furnace went up, that you have to cool the furnace down as well, not just the work that's inside of it. Then most important is the number of units in the furnace, and there are like the Cerac fast fire is only a single unit. And some of the Kima furnaces, there are some models you only do 3 units, some models you can do 6 units. But they're always single units, never bridges. You can never fast fire a bridge. You're never going to get away with that. That's going to fracture. Okay? So you can do fast firing. Depends on what your client is accepting on the aesthetics and what you want to sell. And in a pinch, as long as you have a furnace like this, you could get away with it. Now, zirconia is very inert, which means it's very biocompatible. That's fantastic. There's not going to be any adverse tissue effects to the patient. As a matter of fact, the cements may be more affected than the zirconia. But because it's so inert, it can't be etched like we do dental porcelain. Any cracks can't be healed. You remember when you took a PFM out of there and you saw a little crack coming out on the pontic, you just put it back in the furnace again. Because the glass will free flow, and the probability of getting cracked the second time is very low. But with zirconia, you could bring it in the furnace up and down as many times as you want, the crack is still going to be there. It doesn't heal. It doesn't form a glass. There's nothing to bond it together. None of the chips can be repaired. If you have a chip, you start over again. Zirconia has very poor adherence to porcelain. This is one of the reasons why monolithic porcelain was so popular so fast, because the regular porcelains, which required the porcelain to be, the regular zirconias that required the porcelain to be baked on it, the biggest clinical problem was chipping. And because there was no chemical bond between the zirconia and the porcelain, like there is between alloy and porcelain. Okay? And bonding is questionable, although we have a couple of companies now that are saying that they're getting some bonding, but that remains to be seen. Time will tell. Okay? Now, contouring zirconia. Now, you may think you're not contouring zirconia like this guy, but you are. What is he doing? He's chiseling out a block of marble. and he takes his hammer, puts the chisel against the block at a certain angle that he wants the marble to be at, and he hits it, and little bits come off. Okay? Well, if you remember how we did metal, we took a tool and forced the tool into the metal. What happened? Well, as long as the force was great enough, the metal yielded, it deformed, and the other thing that happened is it increased in temperature very, very fast. But because it was a metal, it was able to dissipate that heat very, very fast. So you just kept going through it, and it got warm, like that 3-unit bridge when you were polishing it, it got warm. That's why you had that little bowl next to the polishing. Just kept dipping it in, right? There's no indication on zirconia. You felt that because the dental porcelain and especially the alloy conducted heat. There's no indication on zirconia. You don't know when that zirconia has been overheated. And when it gets overheated, it's going to transform and it's going to crack. With zirconia, when you're processing sintered zirconia, after it's sintered, you want to adjust a contour, you want to adjust a contact or modify it in any way, you're going to use a diamond. Again, only diamond can damage the zirconia. But when you have that diamond score the zirconia, what happens is that there's a very small region of deformation. What happens to the zirconia is that it forms these little subsurface radial cracks. And it's these little pieces, once they get to the surface, that are coming off. So you're just like that guy with the chisel. Boom, boom, boom. Only you're doing it with a diamond tool. And little bits are coming off of the zirconia. It's not curling off. It's not being processed off like porcelain. It's actually being chipped off. And the biggest danger is you form this median crack. The median crack will always be at 90 degrees to the score of the diamond. Now here we have a case where the unit was given to the dentist, and the dentist wanted to adjust a contact, and he ground on it without using water. Whenever you hand something to your client, always tell them, please use water when you're doing any adjusting. Because if you don't, it's going to crack. Guaranteed to crack. So because it doesn't conduct heat, that's great for the patient. There's no hot and cold sensitivity, even on a root canal case. But you have no indication of the material overheating when you're contouring. Any contouring adjustments of sintered zirconia must be done with water. Hard tools like carbides or diamond discs cannot be used on sintered zirconia because they concentrate the heat, which the zirconia can't get rid of, and it'll force it to crack. Now, you pay a lot of money for your software. And in that software, there are things that you could use that'll make your life a lot simpler. Use the tools in 3Shape in order to minimize the amount of contouring or adjustments you need to have done on that unit. You have libraries, choose the library that's appropriate for the case. There are smart tools in there for both contacts and how the occlusal meets. Use them. I don't want you to design a unit in 3 minutes and 37 seconds like this was done so many years ago. Take your time, because a few minutes here will save you maybe 11 hours later on in redoing the entire case. Don't worry about how you did it with dental porcelain. You have to change your modus operandi with zirconia. Spend more time on design. Use the tools in your software. Let the machine do the milling for you and the majority of the contouring. Don't expect to grind anything in afterwards, because with zirconia, the price you're going to pay is a redo. Okay? Now this is an example of a preparation that had an undercut, And a lot of people think that, okay, if I check that little box on a software, all the undercuts will be taken care of. That's not true. You can actually still develop a unit that has an undercut. And when the dentist tries to put it on in the patient, it's going to crack. So take particular care to block out all your undercuts. It'll make a difference. Because zirconia is a crystalline ceramic, it does not flex. Like if this unit was a PFM, for example, this unit would have went down without any difficulty. Okay, this is one of the units where the dentist does use his thumb to press down and seat it in place. Well, that'll work for a PFM because the metal has some elasticity. It'll open up and then come back down again without disturbing the porcelain. With zirconia, you don't have that opportunity. With zirconia, all that's going to happen is it's going to crack, like this one did. Now this one had another problem where the wall thickness was too thin, but even if it was, because of that undercut, or the way the dentist tried to seat it, it would crack. So again, because it's a crystalline ceramic, there are some factors that play against us when we try and use it in a restorative indication. Now, these are typical zirconia fractures, and as you're probably aware, the majority of fractures that come out are for molars. And why is that? Well, the biting force in a human is most in the molar area. And also, as opposed to interior teeth, like a central, a molar doesn't go into function uniformly. The molar, because of the cusp, the way they're designed, is supposed to be like a mortar and pestle. So by design, it's not going into function uniformly. So different pressures are applied at different times in different areas. And that's going to crack it. Some bits of useless information. So we have a biting force of about 400 newtons. An African crocodile has a biting force of 12,000 newtons. Okay? And they always play with their food before they eat it. Now, the jaw structure of a crocodile is very similar to that of a Tyrannosaurus rex, but only Tyrannosaurus rex is much larger. And on Tyrannosaurus rex, you can calculate the biting force to be 35,000 newtons. So when you could actually crush a car with that. Very interesting, but useless information, as I said. Okay, so we're back to humans. Okay, so 400 newtons. So if we know that our material has to tolerate a biting force of 400 newtons, and we know the strength of the material, so here we have a zirconia restoration with a flexural strength of 1,100 megapascals, and it needs to withstand a force of 400 newtons, then we could calculate what the minimum occlusal thickness needs to be, and that's 0.6 of a millimeter. And where do you find this information? It's in the prep guide. Look at the prep guide from Ivoclar. Look at the prep guide from 3M. Look at the prep guide from Argen. Look at the prep guide from Dentsply. Look at the prep guide from Glidewell. They all say for their high translucent 1,100 megapascal that the occlusal thickness has to be 0.6. How often do you get something that's 0.6? Very rarely, because they don't want to grind away that much. So that means that there's a risk that these molars are going to fracture. If you actually use a super translucent material, then that required thickness has to go up to 0.8. So again, the different zirconias require different preps. And that's one of the things that Dr. Christensen actually addressed. So molars are particularly susceptible to fracture, number one, because that's the highest stress area. And number two, we have a built-in crack starter and the occlusal fossa. Don't try and keep that sharp. Let that round out during the sintering operation, because that will actually stop the crack from happening. Here you have a fracture bridge, again, because they used a disc. And this is from our friends at Glidewell. And if you look at it very closely, you could actually see the formation of the cut that the disc made as it went through. So by trying to open up the embrasures, I know you want to make it look very, very pretty, but where zirconia is sintered, you have very difficult time in trying to open up those embrasures without taking the risk that it's going to fracture. Just be aware of that. Now, the failure rate in ceramics is more possible because ceramics cannot tolerate any tensile forces. Now, when do we get tensile forces? We get it on bridge work. When this pontic goes into function, we produce a compressive force at the top, that's okay, but we get this tensile force at the intaglia surface. That's not okay. That's where the zirconia is going to fracture, or any oil ceramic that's going to fracture. So we have a different way of calculating what the connector size should be. We have our normal that was developed for PFMs, 9 square millimeters for anterior and 12 square millimeters for posterior. But for zirconia, we want to calculate it a little differently. This is thanks to Mr. Glywell, he promulgated this. The height of the connector multiplied by itself, and then you take the distance between the units. That's the width we want. And that number has to come out to greater than or equal to 27. And that'll give you a connector size that'll survive. Any less than that may fracture. So basically, zirconia cannot be designed, contoured, and adjusted like PFM restorations. That's the whole. Now, why zirconia fractures? Because it has 3 different crystal structures. It has this cubic form at high temperatures, has this tetragonal form, then at low temperatures, room temperature, it forms this monoclinic form. The tetragonal form is what we want. That's the strong form. And that's why we add the yttria to the material in order to keep this form. But the zirconia always wants to go back to the monoclinic form. So anytime it has too much heat, like when you're contouring it, anytime you drop it on the floor, anytime it has a little bit of excuse, a little bit of energy is added to it in order to transform it. It'll take advantage of that and it'll transform. So just as we add salt to water in order to stabilize the liquid water, we add yttria to zirconia to stabilize the tetragonal form. But again, at room temperature, it wants to go back to this monoclinic form. So it's always in danger of fracturing. Keep that in mind. It's always in danger of fracturing. And when you try and use a diamond disc, overheat it, you try and do too much contouring without water, overheating it, well, it'll take that energy and transform and fracture. Okay? The biggest reason why it fractures is because it changes the size. Just as water, when you filled your ice cube tray, the ice cubes will occupy a larger volume than the water did. Same thing happens with zirconia when it transforms. It goes from a tetragonal form to monoclinic form. Don't worry about the number, don't worry about the names, but the number matters. The volume expansion is 7%, so it goes pop. And that causes the fracture. Okay. Now, I would strongly recommend you write this down. This is a CRA report from Gordon Christensen's group, October 2018, volume 11, issue 10. They have zirconia, the 5 common mistakes to avoid for dentists. The first thing is inadequate tooth preparation and impressions. I'm sure you're all surprised about that. But there's something very curious here I want to point out. He's indicating that for monolithic zirconia, it's inadequate to have a knife edge margin. But yet that's what we were taught originally when zirconia first came out, that it could also have a knife edge margin. But that was for the high strength zirconia that we're going to bake porcelain on, not for the monolithic zirconia. The monolithic zirconia does not have enough strength to tolerate a knife edge margin. In another study by another group, 95% of the fractures all across the board, regardless of how they were made, whether it was zirconia or PFM, were due to the knife edge margins. So no matter what you're looking at, for monolithic zirconia, we want a slight chamfer edge. Okay? And again, the occlusal reduction is very important and dependent on the type of zirconia that you're using. The other thing is inadequate surface area or roughness of the zirconia internal surface. Now, because it can't be etched with hydrofluoric or phosphoric acid, they suggest not to glaze the zirconia, but rather just polish the surface. I know that may not see well, but you could always keep the area of the unit that goes into function without any glaze and just glaze the facial area. Okay? And for preps less than 4 millimeter axial height, to reduce the digital dye spacer so that the tooth to restoration contact is better. That's another design issue that you may want to take advantage of. And the other mistake is incomplete decontamination after the try-in. Now, after the try-in, there's going to be saliva on the inside, and you got to clean out that saliva. Now, CRA recommends to use IvoClean and with a thorough rinse, and a thorough rinse, according to Ivoclar, is a minute. Not this little, just wash it under there and do it again. It's a full minute in order to get rid of that IvoClean. And if you have a client that continually complains about zirconia coming off, this is probably the reason why, because they're not cleaning out the saliva during the try-in, after the try-in. A misunderstanding of primers. 30% of the dentists that they found, 30% of the dentists that they interviewed were using silane only primers on zirconia. And they don't work. They don't work. But this marvelous little chemical here, MDP, in these in these products do work very well, and they can enhance the adhesion. So Z Prime Plus, Clear Fill Ceramic Primer Plus, and Monobond Plus. That's what they were recommending for that, as far as a primer for zirconia. And then finally, the improper use of cements. Reliex is normally like the go-to material, and for preps over 4 millimeter axial height, that's fine. But if you have a prep that's under 4 millimeter axial height, number one, it really shouldn't be zirconia. It should be a full metal cast. But they're recommending using the newer ones, the Unisam 2 and the Maxam Elite Chroma. And these are relatively new, but they have a very nice little chemical in there that really enhances the chemical strength of the cement. Okay. So for zirconia crack prevention, eliminate any internal surface defects such as pores based on sintering temperature and time. Don't fast cool, that'll cause it to crack. Eliminate any surface defects, no grinding after glazing, and any adjustments require water along with the burr. Eliminate sharp design features, especially the occlusal fossa, and prevent tensile stresses. Use the proper connector sizes in bridge work, especially the height of the connector. Thank you very much.